Hello, this is Kevin Babbitt from the Microsoft Edge team, and I'm here to talk about some changes we made to help trace style invalidations back to CSS rules. Large style recalculations can be a major performance bottleneck on websites. Frequently, these happen because of a state change, which causes a large number of elements to have their computed style information invalidated. Unfortunately, it's not always clear to authors why these large invalidations are happening. Under the hood, Blink indexes style rules into data structures called invalidation sets. These structures tell us, for example, when a given class is added or removed from an element, whether we need to invalidate the element itself, certain descendants of the element, or its entire subtree. So for example, when script sets class G on an element, we look up the invalidation set for class G, and in this case, we see we need to invalidate its entire subtree. But notice that we're only looking at invalidation sets now. Style rules are not in the picture anymore. On real web pages, this can lead to confusion about why entire subtrees are getting invalidated all at once. To solve this problem, we refactored the code that generates invalidation sets. Now that code can also be called in a special mode that retraces the steps we previously took and maps invalidation sets back to the style rules that generated them. When tracing is enabled, we can consult this mapping to connect invalidations back to rules. The result is that now, when an invalidation happens, authors can find out exactly which style rules led to that invalidation. Here's a real example from Microsoft Teams where we discovered that certain first child and last child selectors were causing a large subtree of elements to have their styles invalidated. The Teams team was able to fix this issue with an adjustment to their CSS. We can also aggregate these events for key insights. Here's the output of a Python script I wrote that takes a trace file as input, looks at each style recalc event in that trace, and accounts for the elements in that event by looking back at previous invalidations and counting up which rules were responsible for each of them. The Edge DevTools team is also collaborating with the Chrome DevTools team to land tooling for this feature in developer tools. I'd like to thank Anders and Runa for comments on the design review for this feature, as well as Runa, Alex, and Steinar for code reviews. That's all I have. Thanks for listening and enjoy the rest of BlinkOn.
Hi BlinkOn, my name is Ishika Patel and I am an engineer for Microsoft Edge. I want to reintroduce you to the Get Installed Related Apps API, a powerful tool now available for progressive web apps in Chrome and Edge. Gira makes it possible for a web developer site to check if its related mobile or desktop app is already installed on a user's device. The API has been a reliable tool for both Android and Universal Windows platform apps since shipping in 2020. Since then, requests to check for related web apps have been pouring in from developers. And I'm happy to report that we've expanded support for Gira to also detect these web app installations. It is becoming more common that a developer's native app is actually an installed web app. This is because the web offers a truly cross-platform development surface. Adding additional support to Gira to detect these web app installations addresses this shift in developer focus. When configured with the API, the site can detect if its native app or web app is installed. Based on this, the web developer can coordinate a seamless browser-to-app experience. For example, imagine you're receiving a Teams meeting link in your email. When you click the link, it opens in the Browser tab. Gira enables this Teams site to detect if its web app is installed to offer an Open an App option alongside the Continue in Browser option. To use Gira for web apps, developers must add a self-defining platform and ID entry to the Related Applications field in their web manifest. This demo site is a configured installable web app which uses JavaScript to call the Gira API, then prints its return value if an installed app is there. We've installed this web app, and now the site can check if the web app is installed by calling the API from within its scope. Gira returns a promise with an array representing all installed related apps to the site. We are so excited to present this highly anticipated addition and finally bring parity for detecting installed web apps to Gira. Currently, this new support is gated behind a feature flag. Also, to champion user privacy, we've added a UI touchpoint to the site-specific data dialog, also behind a feature flag. We're working on the intent to ship and are targeting 137 to be enabled by default. Try out the Get Installed Related Apps API for web apps by enabling these feature flags. Thank you for your time and curiosity.
Hi, I'm Myung-Shin from Igalia. I'd like to share my experience supporting extension on Android. Currently, Chromium does not officially support extensions on Android or iOS platforms. Also, embedders that use the Chrome layer cannot use the extension feature. How many folks would like to see extensions supported on Android? Over 1,000 people have started the issue in the bug report expressing how interested it is. Also, it is one of most viewed issues in the past 7 days among extension component issue. It is constantly getting attention from people. I had to partially support the extensions on Android in downstream project. I'd like to share what I did and what technology of extension can be supported through it. First, added enable extension build flag to GN argos. Then you will encounter a lot of compilers. Most of them occur in Chrome layer. Since this build flag is implemented assuming that it is used only on the desktop, not used on Android. To handle this problem, I had to add a new build flag to fix a lot of build errors and link errors. Also, I left the dummy implementations required on Android, and some incorrect build definitions were patched to upstream. After that, when I run extension app, it occurred crash. The problem was caused by different start flow between desktop and Android. So what features of extension could I use? There were many things than I thought. It was able to install, uninstall extension apps, manage the life cycle of them, and execute content script and background scripts defined in manifest. In addition, many APIs except control browser UI worked well. But there were some features and some APIs were not supported. They were not caused by technical limitations. I believe if more time was invested, more API and functionality could be supported. As a result, Light extension app could run correctly, and satisfactory result was achieved with only partial support. However, this approach involved a lot of touching Chromium code directly to fix compilers, which increased the cost of the rebasing. And my approach was not usable for embedder. Can you support extension not only for Android but also for various architectures that utilize Chromium? My idea is have extension in component layer. Just as many other features of Chromium has been moved to components from Chrome layer as a part of modularization, I think this will give more flexibility and reduce complexity and rebasing. This idea is not yet concrete and is still in brainstorming stage. There may be more nice way. If you are interested in this topic, please contact me anytime.
Hello and welcome. My name is Ari Chavukala. I work for Google Chrome, and I'm here to talk about spring cleaning for cookies and storage. So first, let's talk about how website data is stored. Essentially, regardless of the format, whether it's cookies or DOM storage, all of it ends up being files in the profile folder. There are separate profile folders for different logged in users or for incognito mode, etc. So when we're storing all this data, what happens if we store too much? Well, there are limits at the system level, there are limits at the origin level that require purging. Usually that's done by least recently used. But what if we don't hit those limits, but we still have a website we haven't been to in a while, right? What happens if the storage goes stale? Well, first we have to agree on what exactly it means for storage to be stale. The number that we've settled on is 400 days. That's 400 days since the storage was last read or written. The reason we think that's a good number is it encompasses things that happen roughly annually, but assumes that if you haven't visited it in, significantly more than a year, you're probably not likely to do so again, and you might expect the storage goes away. There are exceptions to this, of course. If you mark a storage bucket as explicitly persistent, that's one of the ways to make sure it sticks around for longer. But just for general storage, 400 days seemed reasonable. So how is this enforced? So for cookies, max age cap has been enforced since 2022 on new cookies that were written. And that has been further enforced retroactively in 2023 on cookies that were already in storage. So you shouldn't expect persistent cookies to stick around for more than 400 days after they were last originally written or updated. But for general storage, non-cookie storage, there is a new expiration that has been introduced. And so in Chrome 129, which came out late last year, an experiment has been running to clear storage that hasn't been read or written to in 400 days. And as of this month, this is currently running by default. So this covers IndexedDB, DOM storage, blob URLs, etc. So anything besides cookies is covered by this. Cookies are covered by the previous slide. If you have any questions, don't hesitate to reach out to me. I can't see your questions in the chat because this is a recording. Have a good day.
Hi, my name is Tom Huitem, and I work with the Chrome privacy team. In this presentation, I wanted to talk about a feature that we're currently working on, namely adding noise to canvas readbacks. To start off, I'll take a minute to discuss why we are doing this. So, while GPUs are quite powerful to draw complicated shapes and forms on a canvas, they also produce small variations while doing so. Because these variations depend on the characteristics of the device, they could be used as cross-site identifiers, even when the user is in incognito mode. Our goal by adding noise is to prevent scripts from easily obtaining these identifiers. Now let's dive a bit deeper into how we're applying the noise for the canvas. To start, we're initializing a rolling hash that depends on the embedding context of the canvas. This ensures that if we're applying noise to the same canvas in a different context, we'll get a different output. Using a copy of the rolling hash, we update it with the RGBA values of the current pixel. The hash is then used as the seed of a pseudo-random generator, and we get the location of 2 pixels from it. After that, we update the hash with the RGBA values of those 2 pixels. This makes the noise also dependent on nearby pixels. Finally, we use the rolling hash again to get a pseudo-random value in the range of -3 until 3 for each of the 4 channels, which represents the noise. As an optimization, we check if the current pixel value is an exact match with one of its direct neighbors. If that's the case, we apply the exact same noise. This makes sure that for large patches with the same pixel values, these are also the same after noise is applied. Eventually, after applying the noising algorithm, we get something like in this image. As you can see, it's practically impossible to see the differences between the original and noise versions of these 3 images. Although the noise is not visible in most cases, there might still be certain applications that break unexpectedly because of the noise. And in order to minimize this breakage, we aim to intervene only when necessary. So when the canvas is likely being used to extract an identifier. Concretely, this means that the GPU was used for rendering and a certain number of canvas operations were used. And these are operations that are frequently used in scripts that extract such identifiers, and this may change over time. And with that, I'd like to conclude. So the algorithm that I've shown in this presentation adds noise to each pixel of a canvas in a deterministic way that depends on the embedding context of that canvas as well as its content. In most cases, the noise is barely visible. And finally, we aim to minimize breakage further by only intervening when certain heuristics are met. If you'd like to know more about the feature, I suggest you take a look at the Chrome status entry and feel free to reach out to me or the others on the team, namely Antonio, Enrico, John, and Zainab. Thank you.
Hi everyone, I'm Max from Egalia's Chromium team, and I'd like to share with you 2 improvements that we've recently added to the DevTools mobile device emulation. The first one is the ability to override the small viewport size, and in case you're not familiar with it, that is the viewport size assuming any user agent interfaces that are dynamically expanded and retracted to be expanded. So in practice, this means here on the left we can see the small viewport with the bars at the bottom and the top expanded, and on the right we see the large viewport with those 2 bars retracted. And while preparing this talk, I found this short video that shows why it's important to differentiate between the 2, because in this case, the bar at the top is so big that the button at the bottom of the side is actually off the screen. And so this is currently a protocol-only change, which means we only have a new command in the Chrome DevTools protocol, which allows you to set the size difference between the large and the small viewport. It's marked as work in progress here, but hopefully by the time you're actually hearing this talk, it's already landed. And moving on to the next improvement is the ability to emulate safe area insets. And again, first, in case you're not familiar with it, this is how Safari by default renders a site on an iPhone with a notch, which looks okay, but we can do better than that. The first thing to change is that we can tell Safari to make the viewport actually cover the whole screen, including the notches. But the problem is now content is obscured by the notch. And this is where the safe area insets come into play. You have these insets for the left, for the bottom, for the right, and also for the top, even though it's not shown here, that tell you where it's safe to position your content. So if you combine that with the viewport covering the whole screen, you can have your page look like this, which is much better than what we had at the beginning. And this change is actually twofold. First, again, we have a new protocol command, which lets you override these safe area insets, which has already landed in this part of M136. And then for the front-end changes, we are collaborating with the Edge team, who have written a design doc, which is still open to suggestions, by the way. So if you have any feedback, please do leave it in the design doc. And this is the current mockup for showing you the safe area insets for a predefined device, but it's also possible to add a new device with custom safe area insets. So together, we are now 2 steps closer to accurately emulating mobile devices on desktop machines. Thank you, and also thank you to Polypane for sponsoring this work and to Microsoft for collaborating with us on the safe area inset work.
Hi everyone, my name is Kira Sievers. I work at Google, and today I'll be talking to you about reducing latency with profiling as a case study from Visited Links. So as you may know, profiling is a performance tool that basically tells you how your program is utilizing CPU resources. And in Chrome, this is done with continuous pprof via a tool called Crossbench. And when you run Crossbench in Chrome, you actually need to specify which benchmark you would like to be profiled against. So in this case study, we ended up slightly regressing speedometer 3.0. So in this example, you can see here that we are calling Crossbench via tools/perf/cb and providing our speedometer 3.0 benchmark. There are lots of other things that you can provide, but I want to point out that you can turn on and off your Chrome flag via the enable features as well. So when partitioning is disabled, that Chrome flag is disabled, you can see that the percentage of usage taken up by this function here, determine link state slow case, is about 0.2%. And this is the result of running Crossbench. You get this wonderful flame graph, which shows recursively all the calls being made under your function of interest. Now let's take a look at this flame graph when we enable partitioning. As you can see at this time, when we had the regression, this took up more than the 0.2% of resources. It actually took up 1.5% of resources. And you may also notice that if we take a look at the differences between the flame graphs, the recursive functions that were called under determined link state slow case were different. And this is because we have this other function here, partition visited link fingerprint, which ended up calling schemeful site a lot to construct all these schemeful sites. So what we decided to do was narrow in on this part of the recursive function and see if we could instead cache that schemeful site value instead of having to construct it every time. The result was a great reduction. So instead of 1.5% of resources, we ended up using 0.6% of resources. And you can see that from left to right, it's organized how many resources you're taking up recursively. So you can see we've moved it all the way to the right. Now, to make this even better, we can repeat this process, identify the next thing that we want to minimize, which here was canonicalizing the GURL. So what we do is we identify that part of the code, we improve it. Here in this example, we ended up just not constructing the GURL instead of passing the raw string value. And voila, we've made it back to the 0.2% with partitioning enabled. So what we want to do here is apply this to a bunch of other processes that you might be doing. So if you touch the render aside code and you're a little worried about what the performance implications might be on, say, speedometer 3.0, You can apply the concepts used in this talk to improve your latency on your program. And a huge shout out to C. Bruni for helping me learn this. Thank you very much.
Hi, I'm Jason, and I'm going to talk about improved feature reviews on Chrome Status. For anyone not familiar with Chrome Status, it's the official web app that tracks the development of new web platform features. The homepage is a roadmap that shows what is launching in each Chrome milestone. Other pages show charts of the usage of existing features. And for those of you who are feature owners, your feature detail page helps guide you through the feature launch process. Part of that process is earning review approvals. Chrome Status has been the main tool for API owner reviews and cross-functional reviews for the past few years. Now, we've added a one-icon summary of the review status for each feature directly on the roadmap page. Your feature should have a green checkmark before its milestone arrives, otherwise you may need to reschedule. The purpose of reviews is to speed up the success of your feature, not slow it down. The reviewers do care about being responsive, and we are tracking the times for both their initial response and review resolution. Now, we only count the time that you are blocked on the reviewer, not the time that the reviewer is blocked on you. So, if a reviewer indicates that your feature needs work, you will see this red turntable icon. That means that the clock is stopped and the ball is in your court. You need to address the reviewer's feedback and then press the re-request review button to get the review moving again. It's now possible for some reviews to take 0 time. If your feature has no impact on privacy, you can fill in some survey questions to explain that, and then when you click on the button to request a review, you will have a chance to self-certify. We're already seeing self-certification used quite a bit, and we'll be working with other teams to add it to their gates. This is not new, but I just want to remind folks that the origin trial, creation, and extension processes both go through Chrome Status. So once you clear all the review gates, the buttons become enabled. Then you can fill in some more details, and then that kicks off an automation that sets up the trial. Lastly, I just want everyone to know about some new fields. The estimated shipping year helps people understand how many features ship per year. It gets filled in automatically, and it's updated automatically when you set the shipping milestone, but you might need to edit it if your plans change before you get to the shipping stage. Next, baseline is super important for the whole web platform. To support that effort, Chrome Status feature entries now relate to web features. Thanks for listening, and keep in touch.
Hi, my name is Evelyn Kaplan. I'm from the Microsoft Edge team, and I'm here to give you an update on the ARIA Notify API. The last time you saw ARIA Notify was at BlinkOn 19. I recommend watching Alison Maher's talk on ARIA Notify from BlinkOn 19 on YouTube. She gives a great deep dive into the API there. I'll give you a recap here. ARIA Notify is a new JavaScript API that's designed to replace the usage of ARIA live regions in scenarios where there is no dynamically changing content, and it allows authors to tell screen readers directly what to read by passing a string to be read to the assistive technology, calling document or element.arianotify with the string argument. If the platform doesn't support the API, the browser will fall back to ARIA live regions. What's changed since BlinkOn 19? The valid values of the priority property have been renamed from none to normal, this is the default value, and from important to high. The interrupt and type properties will not ship as part of V1, but we do have implementations for these properties behind a feature flag in Chromium and hope to include them in future iterations of the API. Since BlinkOn 19, the Linux implementation is complete, including a fallback mechanism for Linux versions that use older versions of the ATK library, and you can find that code in the Chromium project. And we plan to create a new permissions policy called ARIA Notify, which would allow authors to opt iframes out of ARIA Notify. The current status of the project is that it's prototyped in Chromium behind a feature flag on Windows, macOS, Linux, and Android, and you can test out V1 and V2 with the ARIA Notify and ARIA Notify V2 Blink feature flags. You must ensure to also enable the UIA provider flag, as this is needed for the current Windows implementation. There is also a draft spec as well as a polyfill that has been worked on by the GitHub team. What's next for ARIA Notify? We're working on the HTML spec change that's needed for the new iframes permission policy, as well as the ARIA and HTML spec updates. We're working with assistive technologies such as screen readers on consistent support of ARIA Notify and live regions. We'll ship UIA in Chromium, and we'll start the origin trials in Edge and Chromium. The goal for that is this month or next month. And thank you to the following contributors for all your help on the project so far. And if you have any questions or feedback, please shoot me an email at evelyn.kaplan@microsoft.com. Thanks for watching.
My name is Jack. I'm from Chrome Device API team, and today I'm going to talk about WebDriver BiDi for Web Bluetooth automation. So what is Web Bluetooth API? In a nutshell, Web Bluetooth enables connection to Bluetooth devices that support generic attribute profile, which is also known as GATT or GET. Upon permissions granted to the site, Bluetooth can monitor for advertisements sent by devices and interact with the device through GATT protocol. Use cases for Bluetooth can be found in STEM education. We have companies like Lego, Vex Robotics, and iRobot Education make educational robotic kits that use Bluetooth to program the robot. We also have use cases in health industry. We have companies like Padora builds healthcare dedicated solutions based on Bluetooth devices and Chrome OS. Next, what is WebDriver BiDi? In a nutshell, the vision behind WebDriver BiDi is to let you write tests using any of your favorite tools and automate them in any browser or driver, giving you full flexibility. Current status for Web Bluetooth automation, more specifically for Web Bluetooth WPT test, is that Web Bluetooth WPT test involving simulated peripheral can only passes on content shell, which is a special compiled version of Chrome that has some tricks like exposing fake Bluetooth simulation module interface and first device select controller. This browser-specific way for automation is not ideal. Why? First, it's hard for other browsers to evaluate the implementation when adopting Web Bluetooth. Second, web developers need to follow these non-standardized setup steps to test their web application against simulated Bluetooth devices. The current public WPT test for Web Bluetooth can be found in the link here, Bluetooth/Legacy. As you can see here, even for production Chrome, it failed on most Web Bluetooth tests because it doesn't have those tricks we mentioned earlier in the content shell. So, the solution to address this issue is WebDriver BiDi for Web Bluetooth automation. Currently available WebDriver BiDi commands and events for simulation can be found here. We have commands for device simulation. We can simulate an adapter. We can simulate a pre-connected peripheral. And we can disable the simulation to make browser go back to normal mode to interact with real Bluetooth devices. And we can also simulate advertisement from Bluetooth devices. We also have commands for chooser automation. We will get an event when chooser is created, and we have command to choose the device we want from the list in the chooser. We've already have some WPT tests that's already been migrated to use WebDriver BiDi. They can be found in the link here, Bluetooth/BiDi. As you can see here, production Chrome can pass those Bluetooth tests. We don't need any specific trick. WebDriver BiDi command can support on production Chrome. For Edge, even though it is a Chromium-based browser, the reason it failed is because it probably needs its own WebDriver BiDi module to cook up the existing Chromium framework. For Firefox and Safari, they have failed because they don't support Web Bluetooth yet. And here is an example for automation code for Web Bluetooth using WebDriver BiDi. So first block, we will simulate the adapter and simulate a device, and then we will do a preparation for device selection. Upon prompt event, we will use another WebDriver bytecode command to select the device. Then go to the test logic, get a result, and validate the result. And eventually, we can disable the simulation to make the browser go back to normal mode to be able to interact with real Bluetooth devices. So what's next? By the end of H1 2025, we plan to support more commands for Bluetooth WebDriver BiDi in order to migrate all of the Bluetooth WPA tests using WebDriver BiDi. And in addition to Bluetooth, as part of the work in 2025 in the ROP Gamepad, we are going to provide WebDriver BiDi support for Gamepad API automation. And that's it. Thank you for paying attention to listen to this lightning talk.